Moment angle complexes, spaces of hard disks, and their stable decomposition.
Well, thank you very much. It's actually a real pleasure to do this and see a lot of friends here. Okay, so I'm going to be talking about three seemingly different constructions that tie in with some fairly naive problems. At least I hope I convince you that they're fairly naive and potentially interesting. So this lecture will include, the first part will be about moment angle complexes, and it's a very short report on work with Tony Bari, Martin Bendersky, Sam Gittler. The second part arose from some conversations with some physicists about a gadget called spaces of hard disks. So I want to try to illustrate some of the similarities and possibly informative properties. And then I'm going to make, or I'm going to present several homework problems and a couple of wild guesses, which are probably wrong. Okay, so that's the content of the lectures. Definitions and main results are sketched next. So the first space I want to start off with is the classical configuration space of ordered k-tuples. That's ordered k-tuples in a product which are all distinct. That is, mi is not mj if I is not equal to j. Now you can imagine that wondering why well, if you haven't seen these things before, you might wonder how could they possibly be interesting. Well, I'll try to convince you of that a little bit. The configuration space of unordered k-tuples of distinct points is the orbit space of the ordinary configuration space modulo the natural action of the symmetric group, which acts by permuting coordinates. So some of these spaces are actually very close to constructions that you've probably seen in high school. So I'm going to say a little bit about that. Let's consider polynomials, that is, monic polynomials of degree k, that is, complex polynomials of degree k. And you can imagine splitting this as a product of linear factors. It's rumored that one can do that. Now, I want to think of the space of all of these polynomials, that is, all monic polynomials of degree k. That's naturally a topological space in several different ways. By identifying a polynomial with its coefficients, the space of polynomials is clearly complex k-space. It's vector space of complex vector space of dimension k, just given by the coefficients. On the other hand, you could identify a polynomial with its roots. So earlier we saw that you could think of the polynomial as split, and so you now have k roots which are no longer ordered. So the resulting space is sometimes known as the k-fold symmetric product. So that's just the unordered k-tuples of points in the complex numbers. Now, by identifying the polynomials with either its coefficients or its roots, you get homeomorphic spaces. You get essentially the same spaces, but by a map which is, has some interesting history behind it. So you can imagine starting off with unordered k-tuples of complex numbers. Think of those as the roots of a polynomial. Well, the coefficients of the polynomial are then given by the elementary symmetric functions of the polynomial up to sign. So there is a homeomorphism which sends the roots, that is the unordered k-tuples, to the coefficients, which is the ordered k-tuples. That's clearly a homeomorphism of underlying topological spaces. And well, inverting that, or trying to invert that, occupied a lot of Galois time. So that very naive map involving very simple constructions has some interesting mathematics attached to it. Okay, well, how does this setting, how does this fit with what I'm about to talk about? Well, I'm now going to digress a little bit by looking at the roots where you assume that they are all distinct. So you can imagine somebody gives you a polynomial with k roots. You could restrict to the polynomials which have k distinct roots. That's exactly this configuration space that I mentioned at the beginning of the lecture. So what we've seen is that if you restrict to the unordered configuration space inside of the unordered k-tuples of points in the complex numbers, what you have is the space of monic complex polynomials of degree k having exactly k distinct roots. Now, again, this looks pretty naive. This space turns out to be hiding some fairly interesting phenomenon, as I think a number of people in this room have discovered at one time in their lives. These naive spaces turn out to be handy objects. So I now want to say a little bit about some of their properties. So I want to now consider another classical object that goes back to the 1920s, namely Artin's braid group. So what I'd like to do is put up a picture before explaining this paragraph. I want to make a picture of a braid. So again, this is something you could tell a young kid about. I might want to look at a braid. Oh, well, there's a braid. Think of three particles, three of them in a plane, moving downward through time. So you can imagine the top of this cylinder is at time 0, and then you have three particles moving down through time to time 1. And now look at the locus of points that those trace out. The condition that these trace out a braid is that at any time t, if you cut this thing, you get three distinct points. That is, the particles never collide at any time. So that's all the braid group is. It's these paths of particles starting at t equals 0, quitting at t equal 1, and not colliding at any time t. Now, that's supposed to be a picture of this first paragraph. So Artin's braid group can be thought, oops, there's a spelling mistake which Peter Landweber did not find. So Artin's braid group can be thought of as the locus of points moving through time, starting at time 0, quitting at time 1, and not colliding at any time t. Artin's braid group with k strands is just the fundamental group of the unordered configuration space. That is, unordered k-tuples of distinct points in the plane, or the complex numbers. And again, I mean, there are some people who do homotopy theory in the audience. I just like to say that this fundamental group is hiding things that are very difficult to calculate, like the homotopy groups of spheres. They're naturally subquotients of the braid groups in a more or less canonical way. So these seemingly innocent-looking objects carry a lot of information. If there are any number theorists in the audience, you guys probably know of representations of Belyi and Ihara in automorphism groups of the giving faithful representations of the absolute Galois group in the automorphism group of the profinite completion of braid groups and free groups. So these things really, in some ways, are hiding reasonably natural gadgets. Okay, so we've talked about configuration spaces a fair bit now. I want to switch to, oh, well, there's the inventor of the braid group. Well, there's a picture of Artin, courtesy of the Mathematische Forschungsinstitut in Oberwolfach. So the next thing I want to talk about seems like a different subject on the face of it. Seems like a completely different subject. And this subject is sometimes called moment-angle complexes. So I want to spend a little bit of time going over the ingredients and the precise definition of what a moment-angle complex is. On the face of it, they'll seem wildly different than configuration spaces. So, what is a moment-angle complex? I want to start off with a pair of CW complexes, or a pair of reasonably nice spaces. So it's a rather general construction, starting off with a pair. And it's actually convenient to look at an M tuple of pairs. It's very convenient to look at an M tuple, that is x1a1, x2a2 up to xmam. Just having that slight change turns out to be quite a handy thing. I realize it's a triviality, but it's one of those handy trivialities. Now, the next ingredient is an abstract simplicial complex with M vertices. So what does that mean? Let me just recall for you. That means the following. Start off with a set of integers from 1 through M. And an abstract simplicial complex is a subset of the power set of the set of integers from 1 to M. So it's just a collection of subsets of 1 through M with the property that, I guess I didn't put the definition in here. Oh, yes, I did. With the property that if sigma is a subset of 1 through M and tau is a subset of sigma, while sigma is a simplex of K, then you require that tau is also in K. So these have a natural kind of hereditary property. In particular, another triviality, the empty set is in any abstract simplicial complex. That's, again, a handy triviality. I'm going to define the length of a sequence I1 through IK to be equal to K. So Peter found another error, I'm sure, at this moment. There's a misprint. Let's go on and we'll see what happens. So I'm just trying to set up the notation to explain a few constructions and how they connect with different bits of mathematics. So I now want to define the generalized moment-angle complex, or courtesy of Bill Browder, this is also called the polyhedral product functor. And its name is zk of x comma a. So remember, K was an abstract simplicial complex, and X and A were either a product of spaces or some collection, pairs of spaces or some collection of pairs. Now, the moment-angle complex, the generalized moment-angle complex, is a union of spaces d sigma, one for each face in the underlying simplicial complex K. And the bits are just products of spaces yi, where the ith space is either xi, if I happens to be in sigma, or it's in the subspace ai, if I is not in sigma. So this is an incredibly naive piece of a product space. Very simple notion of a product space, or a bit of a product space. The moment-angle complex is just this union. It's just a union of these little product spaces inside of a big product. So why would anybody be interested in this? Well, let's push on. I want to give an example so that we're all more or less on the same page, that we all kind of know what an example of a moment-angle complex. So let's start off with a simplicial complex with two edges, 1 and 2. Two vertices. Oh yeah, another mistake. That should be, 2 vertices and 0 edges. Sorry, no, it's correct. It's correct. So we're starting off with 2 vertices, 0 edges. So that simplicial complex, the geometric realization, is 2 points. Something very simple, 2 points. What's the moment-angle complex, zk, of this pair? Well, it's a union of those subspaces d sigma, where the factors are either the disk or the sphere, depending on what the index I is. In particular, when K has two vertices, zk is just the disk cross the boundary of the disk, union the boundary of the disk cross the disk. So that's something really simple that you guys have seen probably as first-year college students. It's a sphere. So this is a naive description of a sphere. Okay, well now I want to give some more examples that have more interesting behavior. I want to look at the moment-angle complex where X, the space X, is just a two-disk, just the ordinary two-disk in the plane, and A, the subspace, is just a circle. So again, this is a relatively simple-looking creature. I now want to talk about this space a little bit, and I want to compare it with complements of unions of certain coordinate planes in complex M space. So remember, M is the number of vertices in the simplicial complex K. Now, I'm going to define a coordinate plane in complex M space in the following way. If omega consists of the vertices I1 through IK, where I ordered these, I linearly ordered these in the previous slide. If I1 through IK are the vertices, then L omega is just the coordinate plane, that is the plane through the origin with the coordinates I1 up to I through IK equal to 0. So we're just specifying a coordinate plane through the origin. Again, seems like a reasonably naive construction. Okay, now I want to define UK to be complex M space minus a union of coordinate planes. Which coordinate planes? It's for those faces, omega, that are not in K. So for every face not in K, consider the associated coordinate plane, take the union of these things, take their complement in complex M space. So that again is a rather beautiful space. It came up many times in many different contexts. In one way that I think is particularly beautiful, Goreski and McPherson, in their book on stratified Morse theory, gave a homological decomposition of these spaces amongst other spaces. And I have to say, the reason I'm talking about this subject here is a complete accident that happened here about 5 years ago. Some of these guys in the third row were sitting in an office. We started talking about this theorem of Goreski and McPherson and how that could be. Well, that's how this lecture today arose. So I want to continue with that. I'm just continuing with this accident that started here about 5 years ago. Buchstaber and Panov observed that the moment-angle complex is naturally a subspace of this complement of coordinate planes. And not only is it naturally a subspace, it's a strong deformation retract. And if I had known that Mike Davis was in here, I would have put in a slide next about the Davis-Januszkiewicz spaces. These are some of the basic spaces that Mike cooked up, and they're one step away from giving the Davis-Januszkiewicz spaces. So I'm missing a big part of the subject by not putting in that reference. That's part of this business. I want to continue in a different way. I want to now restrict to something even simpler looking. I want to let X be a circle, a standard circle in the plane. Sorry about that. And E plus is the upper hemisphere of the circle. So that looks, again, like a reasonably simple gadget. What could that possibly tell you? Well, the space of positions of the following creature is an example of a generalized moment-angle complex. So let me see if I can run a quick picture of one of those. So try to connect this with a moment-angle complex. What you're seeing is one of these moment-angle complexes in action. And if there's more time later, maybe I'll put up a few more.
Theory has more than one leg to stand on.
Right. Right. I'm going to try to maybe run some examples later, but let's push forward in the lecture. So I want to say that this description of legs moving around, this kind of mechanical cockroach, has actually been used by an engineer, Dan Kodacek, who spends a lot of time trying to understand these creatures. Oops. Sorry, let me fix the display. Let's see, what did I do? Full screen. Okay, great, great. I think that I'm just going to go on to the next seemingly different subject, but we'll see at the end that we're really talking about the same kinds of constructions when we're looking at configuration spaces, moment-angle complexes, and right, so why don't we talk about that later, because I have some slides at the end which I hope will draw things together a little bit. Is that reasonable? So think of yourself as a cockroach with 3 legs on one side and 3 on the other. If you had all 3 of your legs, actually let me see if I can demonstrate. So these legs are moving around like this. Think of the head of my cane as the foot of the cockroach. They're moving around like this. Now, if the cockroach has 3 legs poking up in the air on one side, it tips over. So you'd like to avoid that, and that's really what's going on with the moment-angle complex. Okay. So now, what I'd like to do is go on and think about spaces of hard disks. What are those? And again, this was an accident. I happened to be sitting in a room with some people. Maybe it was in this room, talking with some physicists, Randy Kamian and others. This natural space came up. Let me say what I mean. Fix a real number between 0 and 1. And a strictly positive integer where Q, and again, I have the English twisted up, where dn denotes the unit disk. So we're just looking at the unit disk and a fixed real number. And now I want to consider the space of ordered Q tuples. So I didn't put down any symbols, but maybe A1 through AQ, which consists of disks of radius r in the disk of radius 1, which do not overlap on their interiors. So this is the notation for such a space. What this means is we're looking at little disks of radius r in a big disk of radius 1, and we're looking at ordered Q tuples of those. Now that certainly can be empty. If r is equal to 3/4, it's going to be tough to get 2 of those disks in the unit disk. So it certainly could be empty. Anyways, I want to consider the space of hard disks. for various reasons. I haven't told you much of the motivation, but let's push on. Some illustrations are given next. Again, note that the space of hard disks might be empty. Well, there are people who study this problem. Ron Graham, amongst other people. You might try to study disks packed in a plane, or in a disk, or in a rectangle. So there are a number of people here who study this. Matt Cayley, I think Bob McPherson is looking at it a little bit. But they're rather interesting spaces, and I want to try to say a little bit about how they fit together. Let me give another one. There's a picture. Oh, I guess I should say how many disks there are. This particular packing has 31 disks in it. Okay. Whoops. So here's a picture created by Yuliy Baryshnikov. Let me say what this is a picture of. It has more data in it than I had intended at the moment. Think of this black circle as a disk of radius 1 in the plane, just in the plane. Disk of radius 1 in the plane. And now think of 6 small disks packed in the plane where you see they're just touching on the boundary, but they're not allowed to overlap on their interiors. And then, so I'm looking at 6 disks in the disk in the plane of radius r, and I've specified a radius here. R is bigger than 1/4. And it's less than or equal to 1/3. What does this mean? If you're 2 years old, what it means is you could draw a diameter, and you could line 3 of the disks up on a diameter, but you couldn't line 4 of the disks up on a diameter. Does that make sense? Now, it turns out that this has an interesting picture to it. You can imagine having disk 1 and disk 3, and somehow pushing 4 and 2 off to the side, and then swapping 1 and 3. It's a little bit like 2 people trying to go through the same door at the same time, which only occupy, through which or the door can only occupy 1 person. So there's an obstruction. And what this is giving you are this kind of swapping of 1 and 3 and 2 and 4 gives you 2 non-commuting elements in the fundamental group of this space. So they turn out to have some reasonably interesting motions attached to them. Now, this is not packing pennies in the plane. There's a classical problem. This mathematics that I'm going to talk about next does not at all touch on packing pennies in the plane. What it does, packing pennies in the plane is asking about closest packings. I'm not asking about closest packings at all. This is asking about the space of packings. It's asking about the space of packings. And the buzzwords that I want to use are that these spaces admit the moment-angle complexes, spaces of hard disks, and some configuration spaces admit something called stable decompositions. This is in the vernacular of homotopy theory. What I'm going to do is make a digression to say what stable decompositions are and how these decompositions sometimes inform on cohomology groups. One of the motivations is one of the earlier slides. So you remember that Goreski and McPherson gave a homological decomposition of this space. Now I want to say how what I mean by stable decompositions and how that impacts homological decompositions of spaces like this, as well as spaces of hard disks. So I'm going to digress a little bit, talk about stable decompositions, And again, I want to repeat, this has in no way impact classical delicate questions like closest packing questions. All right, what is meant by a stable decomposition? Well, here's a picture. Here's a picture. What you do is you start off with a space. This blue circle is supposed to be a topological space. And then you think of two cones. You think of a cone above the space and a cone below the space, and then glue these cones together. All right, so that's all that this is. You've got a cone point, a cone sitting above a space x, and another cone sitting below it with a second cone point. This is a picture of the suspension. And that suspension in this lecture is written capital sigma. So W is this space in blue. And sigma of W is supposed to be a picture of that space. All right? Now, given a good topological space, and again, this is a purely technical issue. I don't want to even mention the definition of good. But given a halfway reasonable topological space, you could consider the suspension. And one of its properties is that the homology groups of a suspension are essentially the homology groups of the space to start with, except there's a degree shift. All a suspension does to homology is it shifts the degree. It doesn't change the homology as groups, it just shifts the degree. Okay, so now the homology of a suspension gives the homology of the space itself. All right, now I want to talk about some other naive decompositions. These are called wedges or bouquets. A wedge or bouquet of two spaces. Here's what that means. The ingredients are a space A together with a base point little a and big A, and then a base point little b and big B. And now you could imagine looking at the product, A cross B, and now think of the subspace, which is A cross the base point in B, union the base point in A cross B. So it's like the axes in a product. You've just specified the axes. And A wedge B is exactly the axes in the product, where the embedding of the axes are specified by the points A and B. Okay, now I want to talk about stable decompositions of moment-angle complexes, spaces of hard disks, and configuration spaces. So what's happening is that these three natural spaces that we talked about, the space of distinct roots of polynomials, the space of robot legs, the space of hard disks, they all have this common property that if you suspend them, then they start to break apart into these little blisters that are glued together at a single point. So you have a bunch of pieces that are just glued at a single point. This kind of phenomenon goes back 60 years or maybe further. I'm going to illustrate it next with something that you all probably studied in a first course in algebraic topology. Let's think of a product of two spaces, SP cross SQ. The suspension of the product and the suspension of the wedge of these three spheres are homotopy equivalent. The eyes of algebraic topology can't distinguish the suspension of these two spaces. In particular, these two spaces have the same homology. Now, if you're taking a first course in algebraic topology, how would you work out the homology of a product of two spheres? You probably use the Kuhn theorem. Well, you can say, well, I don't need the Kuhn theorem. If I know the homology of a bunch of spheres here, I can just use excision. If you happen to know that these were the same after suspension, that calculates the homology without the Kuhn theorem. Well, that's what's happening with spaces of hard disks, moment-angle complexes, and configuration spaces. They start to break apart. Oh, and I just want to try to quickly dispel a classical myth. Usually you think that when you suspend spaces, you lose information about the product structure in cohomology. And it turns out at first glance you do, but at second glance there's something hiding there. Okay, well, now I want to look at examples of stable decompositions. The first one is our friendly, our friendly configuration space. So this means ordered k-tuples of distinct points in the manifold in Rm. So again, this looks pretty simple. We can ask, what is the suspension of this space? It turns out it's a bunch of spheres glued at a single point. And the number of spheres, well, there are A1 of them. I haven't told you what A1 is. There are A1 of these spheres of dimension m minus 1. There are A2 of them of dimension 2 times m minus 1, up to AK minus 1 of them of that dimension. Now I'm going to specify the integers. The integers are given in a classical way via a generating function. In particular, the integers for those wedges are specified in the following way. Start off with a polynomial, which is just the coefficients. The coefficients are just those AIs. They're the number of those particular spheres. Or take the product, 1 plus t to the m minus 1 times 1 plus 2 times t to the m minus 1, continue, up to 1 plus k minus 1 times t to the m minus 1. So that specifies the number of spheres, it specifies which they are, and it tells you that if you suspend this very natural space, it breaks apart into a bunch of little blisters, which you think you know about. Okay, now I want to talk about the next example, namely generalized moment-angle complexes. And what Tony, Martin, Sam, and I did, this is prove the following. But I want to say, before somebody starts complaining, this is a single special case of a very general theorem. Moment-angle complexes always somehow break apart like products if you suspend them. One case are these moment-angle complexes based on the disk D2, S1. The suspension of this space is a wedge of suspensions of geometric realizations of, another misprint, of geometric realizations of subcomplexes called Ki. What this means is that these Ki's run over the so-called full subcomplexes of K for I not in K. So what this is telling you is that the homology, if you're interested in such things, if you're interested in the homology of a moment-angle complex, it has to break apart. And the formula for the answers are given precisely by a relatively complicated combinatorial formula. You need to know what the full subcomplexes are. And I have to admit that I don't really know how to precisely compare the formula of Goreski and McPherson with this formula. I don't really know the precise translation. Now, presumably there is one. So another feature of this is that this tells you about things other than singular homology. You might want to know about K-theory or Bordism theory. What this tells you is that any homology theory for the moment-angle complex breaks apart. And this is actually how I got involved in fiddling with robots that I'm going to illustrate shortly. It's because of these cells that somehow come up, and you want to try to somehow understand vector fields on those things. Okay, now I'm going to talk about examples of decompositions for spaces of hard disks. And these remarks arose with conversations, most of which were in this room about 2 months ago, with Matt Cayley, Yuliy Baryshnikov, Randy Kamian, Gareth Alexander, and Brian Chen. Randy, Gareth, and Brian are physicists. They're not mathematicians by trade. Well, maybe. Well, I shouldn't have said that. That's not accurate. Anyways, they're physicists, or they say they're physicists. That's right. That's a better way. That's exactly right. Okay.
That second comment gives you quite a lot of credit.
Oh, well, in fact, I would make a conjecture. I'd send it off to these guys, and the next day there'd be a counterexample. So that may continue in the next few slides. All right, so the next description is imprecise. I'm trying to convey an idea of a kind of degree of freedom in a hard disk. Now, I want to say that the space of hard disks is L good. So I'm defining something which is still imprecise called L good. L good basically means the following, that L is the largest number of planets in orbit around a disk. That is, if you fix a disk, you can imagine having a planet in orbit around it, and then another planet in orbit around the sun and the first planet. You can imagine having a family of concentric circles in which these things move around. But they don't have to be circles. They could be kind of tortured paths. They could be basically paths along which you do a Dane twist and imagine moving these things in orbit around themselves. Now, I've been imprecise about that. If I'm willing to be more precise later, but not on the slide. So you now have a vague idea of what L good is. Let me give you an example. Let's look at that earlier slide of 6 hard disks of radius a third. Well, you can imagine taking 3 of these disks and kind of pushing them off to the side, and then having this disk as the sun, having number 2 moving in orbit around the sun, and then having number 4 moving in orbit around those 2 somehow. Again, I haven't been precise about that. I'm leaving this up to your imagination. But that's roughly what the idea of L good is. Now, here's an example. Suppose n is bigger than 1 and the space of hard disks is L good. Then it turns out that this is an observation that the space of hard disks, when you suspend it once, splits. It splits as 2 blisters put together. One blister is the suspension of the configuration space that we discussed already of L plus 1 points in Rn, where n is the dimension of the disk, and L is indicating that the space of hard disk is L good. So you can sometimes split pieces of hard disks or split various configurations off of spaces of hard disks. You can imagine having many solar systems somehow being put in the space of hard disks. You get more and more pieces splitting off. And you can imagine passing to limits and asking what happens as you try to fill up hard disks with smaller and smaller hard disks. I'm going to talk about that for a few minutes. So here's a first crude estimate. Let delta be the largest integer so that R delta is less than 1. What was R? Wasn't R the given radius of the hard disk? So now look at the product R delta. I want delta to be the largest integer so that R delta is less than 1. The only examples that I can work out, and there are a pile of them, is that the cohomological dimension of the space of hard disks. That means the highest dimension in which this thing can have cohomology is, at least for the 2 disk, is bounded above by delta plus 1. So it looks like the cohomological dimension of the space of hard disks is bounded above. The cohomological dimension may be the cohomological dimension of something trivial, like a point. It depends on the particular space of hard disks. Tony?
Is L a maximum value? I mean, if something is L good, is it good for an L less than that?
Yes. Yes. So I should have said it's the maximum. Right. Right.
But you can't split them all at once.
No, no, that's very tricky. And in fact, I'm going to make a screwball guess at the end about that. Okay, so the cohomological dimension of the space of hard disks in any of the cases that I can calculate for the 2 disk is delta plus 1.
So Fred, so from that theorem you have, so when you're L good, it looks like, as far as it's concerned, the orbiting spheres and that when it's orbiting behave like distinct points in the space.
I didn't understand it.
Well, you're getting the configuration.
Right. So I'm going to mention that. You're anticipating the next slide. The space of hard disks is a subspace of the configuration space. Well, can you ask that question?
I forgot it already.
No.
Is the sun intended to be fixed in this?
No. This is a movable sun. So you can actually think of these motions as somehow being given by a point moving along a curve dictated by a Dane twist on a surface.
So it's characterized in the configuration space by some path.
That's right. That's exactly right. I didn't want to say that too precisely on the slides. Okay. So are there any cohomology classes above dimension d plus 1? I mean, people may know that already. I don't know them, but it may be known. And in the other cases, for an arbitrary n, you might guess that the cohomological dimension is bounded by delta by the same integer plus n choose 2. Why n choose 2? Well, I've picked this space of hard disks to be invariant under the action of the rotation group. What's the dimension of SON? That's where the n times n minus 1 over 2 comes in. So that may or may not contribute. I don't want to respond to that, but that's why I threw in that number. The answer is the cohomological dimension bounded above by delta plus 1. The answer is yes in many cases, but q equal 10 to the 23rd looks tricky. And that's supposed to be a joke. When you talk to these physicists, they always will ask you, what about 10 to the 23rd particles or 10 to the 23rd disks? Okay, I guess it isn't a joke. All right, here are some natural maps. Here's some natural maps. The space of hard disks is actually a semi-algebraic set in the configuration space. It's just a set of points. It's just a set of points actually in the unit disk in Rn, which you can think of as the centers. They're at least a distance of r from the boundary. So that means they're just points in a disk of radius 1 minus r. They're just points in a disk of radius 1 minus r. They're distinct, and the distance between any two is at least 2r. So that specifies these in a very simple way as a semi-algebraic set. And a homework problem is to work out the homology of that. Well, it's not so easy. So there's another map. There's another map, which I think I'm going to illustrate. Oops. I'm going to illustrate another map. I'll go back. Sorry to skip ahead. There's a map called BV, which I'm going to describe in a moment. BV for Boardman and Vogt. Boardman and Vogt invented a space called the little cubes, which isn't the space of hard disks, but it's pretty close. Look at a point in the space of hard disks. Well, you can imagine taking this point and taking the complement of the interiors of every disk and collapsing those complements to a single point. What do you get? You get a bunch of spheres glued at a single point. This gives you a map. It gives you a map from the n sphere to q spheres glued at a single point. Now let me go back. There's a second map, which I'm going to call BV. Well, I've already described the map for you. You take the complement of the interiors of the disk, collapse it to a point. That's a little bit like Pontryagin-Thom collapse, but in a parametrized way. This now gives you a function. It gives you a function from the n sphere to a wedge of n spheres glued at a single point. So it's actually a rather natural collapse map. What does this have to do with the homological dimension? Well, actually, I'm going to skip this slide. You probably aren't interested in how these splittings work. Or, well, you might be, but I can't really say much in one slide. Here are homework problems. What's a good bound on the cohomological dimension of the space of hard disks? Is it actually that wild guess earlier in the lecture? Can you identify tractable, reasonable subspaces? Well, we already saw some reasonable subspaces arose from planets in orbit around other planets, and how those gave little blisters, blistering off the space of hard disks. So that's what I mean by tractable subspaces. Are there spaces that you can understand, subspaces that you can understand in some reasonable way?
Wouldn't you expect something catastrophic to happen in the geometry as R and Q?
Oh yes, absolutely. These things they just go crazy. If you start off with small radii, then many people, years ago I think, had proven that these were homotopy equivalent to configuration spaces. But as you blow up, or sorry, I shouldn't use that word, as you expand the radii of the disk, what happens to these things? Well, take a look at that. Can you expand those disks anymore? What is the space of hard disks there? Well, you basically take this particular packing, let SO2 act on it, and quotient out by fixed points, or the isotropy. So you get almost nothing in this case. But if you did something screwball, like fixed one of these, and inside one of these disks put in another little hard disk where disks can move around, you get some space with a larger number of hard disks. And you can ask what you get by kind of inserting little disks with more and more solar systems moving around. So I'm just about to finish. I'm going to respond to your question in a moment. So the next question is the suspension of any path component. So I didn't really emphasize this. These spaces of hard disks are not path connected. You can imagine taking a disk and having some ball bearings tightly packed around the exterior. Well, there isn't much degree of freedom there. They basically can't move except for the rotation group. Now you can imagine taking one of those ball bearings out. If they're sufficiently small, put it in the center, and what you get is something that's essentially the configuration space. So these path components change wildly. Is the suspension of any path component a retract of the suspension of the configuration space? So remember, the space of hard disks is a subspace of the configuration space. In all the examples that I could ever work out completely, the answer is yes in this case, but I think it's likely the answer is no. It's just that I can't work out very many examples. So I think that this, and then we talked about this map from the space of hard disks to loop n, this function space, this huge function space, loop n in a wedge of spheres. And my belief is that this is a stable retract of that one. And these spaces have been studied very intensely. Quite a bit is known about them. The combinatorics is interesting. The topology is interesting. Please remember to hand in the homework. So I should say this last property of inserting smaller and smaller solar systems inside of various disks gives you a space which I think in the end is just essentially the n-fold loop space of the n-sphere. I think it has a kind of natural, classical, relatively understood limit. Again, thanks very much. It's related to the Reith product. That is, suppose you take a look at the group, fix a group G, and think of the n-fold symmetric group, and then think of the group sigma n Reith G, then that's a semi-direct product. It's a split extension of sigma n with kernel G to the n. Think of the diagonal G in G to the n. So that's a classical algebraic construction going back, a long time. But there's a topological version of this. The topological version of this is you take these spaces of hard disks, fix some kind of solar system, and stick it in each one. I think that's what Martin means by the Reith product construction.
It's an iteration.
It's an iteration. So in the limit, now you have to be a little bit careful. If you do this kind of iteration using 31 disks, 31 is rumored to be an odd number. And it turns out that what you basically get is loop NSN with 31 inverted, whatever that is. I don't want to go into this in much technical detail, but I thought maybe I'd try to run an example. And let's see if I can get this to work. Oh, well, too bad. It didn't go straight. It should turn around.